Hi everyone. In this video we're going to talk about degenerate perturbation theory. I'm going to quickly outline the problem and go straight into an example. In a later video I'll do it a little bit more formally and explain a bit more of the mathematics about it. So this is outlining the problem. Consider that we have a perturbation lambda v, as we did in the previous videos. Lambda is a small parameter. And it acts on a system with unperturbed states, and these don't have all the unperturbed states, like there could be more states, but these two states are degenerate with each other, psi A naught and psi B naught. They're both eigenstates of the unperturbed Hamiltonian H naught with eigenvalues which are equal to each other, equal to some E naught. And they are orthonormal by construction. So even though they're degenerate, they are orthogonal to each other and they're both normalized. So psi A naught and psi B naught are orthonormal. So let's have a think about what happens in non-degenerate perturbation theory. So we take one of the wave functions, and what we're going to do is see how it's changed by the addition of this perturbation. If we use the technique that we learned earlier, which is normal perturbation theory, then the first order correction to the wave function, psi A1, can be written as follows. Psi A1 is equal to the sum over all states M which are not equal to A of psi m naught lambda v and I think I wrote this in the last video as lambda psi A1, so I'll do that here as well. So that's the lowest order correction to the wave function, the first order correction to the wave function. And then if we look at this, we have a problem because for the case where we have m equals b in the denominator, it blows up. We have a 0 in the denominator, and so that term is going to go infinity unless the numerator also goes to 0. And in fact, that's precisely what happens. So how can this occur? For our case with twofold degeneracy, what we're going to do is we're going to find two new eigenstates of H naught with the same energy, which are linear combinations of psi A and psi B, such that VAB is 0. And so that will allow the numerator to go to 0, and that will allow us to lift the degeneracy when we apply the perturbation. So I'm going to show you what happens in an example, but first let's just explain a little bit more what's going on. So the two states that we're going to find are going to be psi mu, which I will write as alpha times psi A plus beta times psi B. And obviously this state is also going to be an eigenstate of H naught with the correct energy. And I can write one more. And we want to do this in such a way that V mu nu, which remember is just is equal to 0. So if we have this set up, then normal perturbation theory is okay, because the numerator will go to 0 at the same way that the denominator goes to 0. Perturbation will break the degeneracy so that the shift in energy for the mu state is not equal to the shifting energy for the new state. And so they end up having different energies. All we have to do for this to work is to find the good eigenstates psi mu and psi nu so that v mu nu equals 0. So that seems a little bit esoteric at the moment. So what we're going to do next is going to do an example which should help us out. And I'm going to use one of my favorite systems for an unperturbed perturbation theory problem, which is the infinite square well. Why do we like that one? Because we know the solutions and they're easy to manipulate. So the 2D infinite square well that I'll choose will be a simple Hamiltonian u of x, y is equal to 0 if x is between 0 and a and y is between 0 and a, and it's infinity otherwise. Okay, and for this case, you can go and find the eigenstates yourself, or you can just write them down. A reminder that if you're in an exam situation and I ask you just to write them down, then you don't need to derive them. You can just write it down. So it's easy here because we just have effectively just two 1D oscillators, nx and y greater than or equal to 1, and then the ground state is non-degenerate. By the way, you can check that that's correctly normalized, etc. The ground state is non-degenerate. So if I asked you a question about what happens to the ground state under a perturbation theory, i.e. when nx equals ny is equal to 1, then you don't have to worry about degenerate perturbation theory. But if you look at the first excited states, there are two of them with the same energy. So there are two first excited states, nx equals 1 and y equals 2, and nx equals 2 and y equals 1. They both have the same energy, and just for simplicity, we're going to call these psi a naught and psi b naught. And this is what they look like. I've just knocked these up in Mathematica, and I'll put the code up on the lecture notes so that you can have a look how I did those. But these are the unperturbed functions psi 1, 2 and psi 2, 1. If I put some little axes on these, we'll work out which one's which. Hang on. So we'll put a little arrow there. That can be the x-axis, and this can be the y-axis. X-axis, y-axis. And we see actually that there's only one excitation in the x direction on the right hand side, and it's the second excitation in the y direction. So it's actually this one over here is psi a naught, and on the left hand side here there is a excitation in the x direction and no excitation in the y direction, so that one is psi b naught. But that's what they look like, and they're degenerate with each other clearly. So take this, and now imagine we have a perturbation at one point in the xy plane. So it's a very similar problem to the one that we had before. So we have a very small parameter lambda and a delta function just saying that we have the perturbation only applied at x equals a on 4 and y equals a on 4. So a quarter of the way along and a quarter of the way up. And in my head, I'm thinking about this, you can think of this in sort of a classical way. Those 2D sheets that you see here, which are not sheets, they're just, they're just the wave functions themselves. But imagine that you had a square piece of drum or something like that, something that makes a noise or that shakes. And imagine that you've got these two modes of excitations. This is kind of coming back to kind of a classical physics way of thinking about it. So you've got these two modes which are degenerate with each other, and now what you're doing is you're putting a tiny perturbation at one point on the drum. So you're putting your finger a quarter of the way along the x-axis and a quarter of the way along the y-axis, so just around here somewhere. Yeah, and when you put it there, you cannot have an excitation at that point because that point is now being damped by your finger. So then let's have a look what happens to our matrix element. VAA is equal to the integral. It's a double integral because it's in 2 dimensions. And it is sine pi x over a sine 2 pi y on a squared lambda delta x minus a over 4 delta y minus a over 4 dx dy. And of course you have to take these integrals between 0 and a. And integrating delta functions is easy as it was before. You just take the value of the integrand at the point x equals a on 4 and at the point y equals a on 4 here. And so you can do one at a time and you put them together and you should get lambda 4 on a squared because that's squared, sine squared pi over 4, because when x equals a on 4, then pi x on a will be pi on 4, and then sine squared pi on 2, sine of pi on 2 is equal to 1, sine of pi on 4 equals 1 over square root 2, so we square that, it's going to be 1 over 2, so this is going to be 2 lambda over a squared. And similarly, homework, check it yourself, VBB is equal to 2 lambda over a squared, and you'll also find that VAB, which is the off-diagonal term, is equal to 2 lambda over a squared, which, and this is important, in fact it's crucial, it's not 0. And so because that numerator is non-zero and the denominator is going to be 0 in that first order correction to the wave function, then we don't satisfy the requirements of perturbation theory. So remember when we wrote down in the last lecture, we wrote that one of the rules of perturbation theory was that the perturbation VAB had to be smaller than EA minus EB. So the energy gap should be large compared to the changes in the energy. And so here that's not the case. The energy gap is 0. So it doesn't matter how tiny this lambda is, it's going to be, it's much larger than 0. And so that's why we have the failure, and that's why we need to use degenerate perturbation theory. So what happens if instead we just write so I'm going to choose a different basis here, and psi plus or minus, instead of mu and nu, I use plus or minus because it then makes it really clear, as you'll see in 1 second. So it's a linear combination of psi A and psi B, unperturbed. The plus sign is obviously for plus, the minus sign for minus. And then what happens is that VAA, VBB, V++, V-, all the same. But psi plus naught and psi minus naught is equal to 1/2, because it's 1/√2 squared, psi A plus psi B V psi A minus psi B, which is equal to 1/2 VAA. So now take the first term, psi A, the second term, VBA, the third term, VAB comes with a minus sign, the fourth term, VBB comes with a minus sign. Oops, that shouldn't be square, that should be round. And that's equal to 0, which is what we want. So this is the correct basis, if you like, for this problem. So this is the good basis, and first order perturbation theory tells us that for these good eigenstates, we're going to have delta E plus 1 is going to be equal to psi plus lambda V psi plus, which equals 4 lambda over A squared. Check it yourself at home. And if we look at the minus, oops, that should be first order correction, to the minus state, then we'll have psi minus naught lambda V psi minus naught equals 0. So in other words, we looked at the first order correction to the wave function to work out what the good eigenstates are going to be, but then we go back to first order perturbation theory for energy, and we see that actually they have different energy. The two eigenstates have different energy shifts. So in other words, the perturbation has lifted the degeneracy. In energy space, you have, as a function of the strengthening the perturbation, you have the original value here, E naught, and psi minus doesn't move as you increase lambda, but psi plus does move. So psi plus is no longer the first excited state, but it's now the second excited state. And the first excited state is actually just psi minus. So what does that look like in terms of the wave functions? We see that one of these wave functions has a node at the point a over 4, and this one is moving, so there's a shift in the wave function there. So if you put your finger here, what happens is it will move around this line, and this one is going to move over the line, so this one's 0 along here. So when you put your finger, you select one of these to have a higher energy than the other. So which one's which? The one that has the lower energy is the one where your finger doesn't affect the ground state. So this one here is psi minus. When you put your finger there at A on 4, then it has to push against that perturbation, and so this one here is psi plus. And so in this way we see that the degeneracy has been lifted between the two when you have a little perturbation along the line x equals y. So next we're going to do it formally in the next video.